before we dismissed last week, we had started talking about a technique called separation of variables. Differential equations that are separable. In other words, where you can separate the x's from the y's. You're still going to use integration to solve them. To find your solution, you're going to use integration, but the first thing you have to do is separate all your x stuff on one side, all your y stuff on one side. And I showed you a couple of examples of that. Let's do a few more. This was just kind of the run through of once you get the variables separated, then integrate both sides. All right, this is one we've seen before. Y'all have seen this differential equation. We looked at this when we did direction fields. We looked at it when we did the family of differential equations or the differential equation for a family of curves. We saw this again. This is also an initial value problem because they give us a point here, y of 4 equal to 3. So as far as algebra goes, what would you guys do in order to get the variables separated here on this problem? Multiply dx and y on both sides. Could you, since it's just a fraction equal to a fraction, could you cross multiply on this one? You remember from algebra you could do the cross products equal to each other. So let's do this. Y times dy equals, I'll keep the negative with the x, negative x dx. So that was really easy to separate out, just cross multiplying on each of them. So in this case, I'm going to integrate both sides. Once you get them separated, you want to integrate both sides. So what is the antiderivative of y? So y squared over 2, good job, plus c, but remember I just want to put the plus c on one side because you can collect all your constants together as one constant. So y squared over 2 equals the integral of negative x dx. So negative x squared over 2. And like we said, we needed a constant, so we'll say plus c. Now, it's always, I'm not going to say always, it's usually better if you can solve one of these equations for an explicit variable. Solve it for y in terms of everything else, which would be pretty easy to do on this. But in this case, I think it makes more sense to us to write it in a different way, the solution. That is the solution. As far as solving, you're done. Anybody see anything that can make it a little bit better, maybe? Can I multiply through by 2? Clear all the constants by multiplying through by 2. So y squared equals negative x squared plus 2c. Do I need to put 2c? Can we just call it still just c? It would just still be, we'll make it even better. We'll call it c1. It'll be more sophisticated. 2c is still a constant. If you wanted to solve that for y, then you could do plus or minus the square root of the right side if you wanted to. That's correct. But something even better. What if I just pull that x squared over there with the y squared? What is that the equation of? A circle. Centered where? At the origin. C1. How do you find the radius of your circle? Square root of whatever that constant is, right, would be the radius of your circle. But in this problem, we can't have a C1. Why? Why can I not leave C1 in there? You're given that initial value, absolutely. And, you know, y'all are going to have to be really good and attentive when you're doing your problems, especially on a test, to make sure that you don't forget about an initial value. They don't all have them, but some problems do. And I catch myself messing up and forgetting about the initial value. So you might want to, when you take a test on stuff like this, you might want to look through and see the ones that got initial values and maybe put a little star by it or something that's going to help catch your eye, to help you remember you got to go back and do this. So if I use that initial value, x will be 4, y would equal 3. So let's do that right here. So 4 squared would be what, 16? Y squared would be 9, and that's equal to C1. So what is C1 equal to here? So a solution curve that would go through the point 4, 3 would be the circle x squared plus y squared equals 25. Or the centered at the origin circle with radius of 5. If you were to draw that up there, it should go through the point 4, 3. See, to me, it was dumb to try to solve that one for y because we know it more. We're more used to it looking like this, right? That makes more sense to us because of all of our algebra background and everything. Okay. Here's another separable equation. First time I saw this one, I was scared, but it really works out kind of nice. First thing I'm going to do to separate the variables is I'm going to multiply the dx on both sides. Okay, what would you guys do next? Okay, sine of x is okay to stay over here on the right, right? So this whole quantity, there's no x's in there, so I could divide that the whole parentheses out of both sides. No x's involved in that at all, so they can just divide away. So I will have 1 over cosine of 2y minus cosine squared of y dy equal to sine of x dx. Now, in looking at that, that left side looks almost impossible to integrate the way it is, especially. So, this is why I'm doing this example with you. Can anybody remember an identity we could use for cosine of 2y? Does anybody remember those or have them written down somewhere or a book to look in? You may remember calculus book or PE class, possibly? Yay, Zach's got it. Give me a substitution I can put in for cosine of 2y. Cosine squared minus sine squared is a substitution for cosine of 2y. Okay? So I could say that this right here is cosine squared y minus sine squared y. That's an identity. So what's going to happen there? Those are going to subtract off, aren't they? So that was going to subtract with that one. So I end up on that left side with 1 over negative sine of y, sine squared y dy equal to sine of x dx. What's 1 over sine? Cosecant, and it's negative here, right? So negative cosecant squared y dy equals sine of x dx. So now I'm ready to integrate. I think there is actually a rule for the integral of cosecant squared. Somebody look that up for me. You should have it on your cheat sheet. I don't know that you'll need it, but it's someone I would write down because I don't know it right off the top of my head. Okay, hang on a second though. That's just for cosecant squared, right? Your rule is for just cosecant squared. So what would it? You'd have to change the sign of it if you got the minus, right? So what's that going to give me? Cotangent y plus c, but I'm going to leave that to the right side, equal to, what is the integral of sine x? Okay, plus our constant 1. Now, any ideas how to get y by itself? If you could solve it by y for y? Cotangent inverse of both sides. That's horrible. It's correct. You get a smiley face by your answer on the test from me. But cotangent inverse is not even one you calculate. So is it necessarily helpful? Not really. No, unless you're just a short enough nerdy mathematician that knows how to calculate all that. So you know what I would do on this? I would just say, Eureka, Houston, we have a solution. That was not a good one to try to solve for y. You could do it, but it wouldn't necessarily be all that pretty. And I'm sure that cotangent inverse has all kinds of restrictions on its domain and range. So you'd probably have to put some notes out here beside it to be completely correct. That your x has to be between so and so and so and so and all this stuff. I just say, let's leave it like this and be happy. And this one was not an IVP either, was it? No initial value. Yes, sir.
So wouldn't you be able to lift the cotangent and like multiply by the reciprocal of it and just cosine over sine and then multiply to the other side? And then you have y by itself?
The y will never be able to be detached from the trig function without an inverse trig. Without an inverse trig, that wouldn't work. Remember that trig functions have to have an argument. See, if you did cotangent inverse of both sides, cotangent inverse of cotangent y, that's the only reason that they could go away. Otherwise, you wouldn't be able to separate them. So, hey, don't make a mountain out of molehills. Just leave, if that looks pretty enough to suit me right there. When I'm grading papers, a lot of times you'll see differences in people's work. I may have somebody turn in cosine of x minus cotangent of y equals c. Are they correct? Yeah, same thing. Or some variation where all the signs have been changed. Some little thing that goes on in that problem. So there's a lot of leeway on these problems. Now, if it's just one that's so obviously easy to solve for y, then you probably should do that. All right. So let's work the problem. This one, I found, it is hideous. And so this is going to take us a while, and I'm not even going to record the solution. We're going to work this out on the board here. If you miss class, then you don't get this joyful experiences here. We're going to work this together. This course is going to be full of models. I've got some examples of different models here for you. Mathematical models that are expressions of differential equations. How many of you all have already taken physics? 1 and 2. Okay. Anybody taking modern physics? All right. In science and engineering, we often wish to describe or model a phenomenon or physical system in mathematical terms. This description starts with identifying the variables that are responsible for changing the system and a collection of reasonable assumptions about the system. These assumptions will include empirical laws that are related to the system. The mathematical construct of these assumptions is often a differential equation whose solution should be consistent with the known behavior of the system. So one of the most famous models that's a differential equation, remember, a differential equation is an equation with a derivative in it. You guys learned in Cal 1 that acceleration is the second derivative. If an object is falling we know that it falls with acceleration due to gravity. What is that gravitational constant? 32 feet per second. Is that right? What is the metric one? 9.8 meters per second squared, and it would be negative, wouldn't it? Okay, for a falling body. The mathematical description of a falling body under the influence of gravity leads to the simple second order differential equation. How do I know this is a second order? It's got a second derivative in it, right? Second derivative. It is well known that free-falling objects close to the surface of the earth accelerate at a constant rate g. Acceleration is the derivative of velocity, which in turn is the derivative of distance. Suppose a rock is tossed upward from a roof of a building. If we assume that the upward direction is positive, the mathematical statement, second derivative of s with respect to time, s is always your position function, is negative g. That's a differential equation. So that's one mathematical model. We will revisit this in just a second. Okay? Here's another one. Spring and mass systems. Newton's second law is combined with Hooke's law. I know we did Hooke's law in Cal 2. We can derive the differential equation governing the motion of the mass attached to a spring. Classic model. Y is the displacement. T is time. M is the mass. A is the friction or the damping constant, K. K is the spring constant. F of T is a forcing function. I would think that either you'd have to figure out what all those parts are, or you have to be given them for the problem that you're dealing with. Variations of this model can be used in problems ranging from shock absorbers on an automobile to answering questions about the human spinal column. Was it one of you that did their project for me on their knee? Hooke's law, they did. It's out here in the box if you want. It's Hooke's law on the stretching of the tendons in the knee. Pretty neat. What type of equation is this, by the way? What order is it? Second order. Is it a linear equation? It would depend on what? Second derivative, that's okay. First derivative, that's okay. Y to the first power is still okay. If your coefficients, though, ended up having y's in them at all, that makes it nonlinear. Or if any derivative is ever squared or cubed or anything like that, that makes it nonlinear. If this forcing function over here has a y involved in it, it is nonlinear. For example, if this was cosine y, cosine of y, that's not cosine times y. Cosine y is a function in terms of y. It would make it non-linear. I just said that for a specific reason. Okay? If this forcing function over here is in terms of y's, it's non-linear. Okay? I am the dumbest person on earth about this kind of thing. How many of y'all are going to be electrical engineers? Anybody? Well, y'all must be as dumb as me then. No. I am stupid about this electronics and electricity stuff. But this is a model. We'll actually do some problems this semester with circuits. Okay? But I'll try to make it to where everybody understands what's going on. According to Kirchhoff's second law, the impressed voltage on a closed loop must equal the sum of the voltage drops in the loop. The current in a circuit after a switch is closed is denoted by I of t, another function of t. The charge on the capacitor at any time t is denoted by Q of t. The letters L, C, and R denote constants known as inductance, capacitance, resistance. Have y'all studied that in physics? Did y'all do all that? Okay. So, putting all that together, adding this inductance, resistance, and capacitance there, the parts of that together, you get the impressed voltage. So all that forms what type of equation? classify that equation for me. Second order, possibly linear. I think probably so, always. I think those R's, C's, and stuff are always going to be constant, so that's going to be linear. And is it partial or ordinary? Ordinary. Remember, y'all don't miss that on the test to put partial. The only time you ever have partial is if you got that little swirly looking differential sign. Y'all ain't even doing that in this class, okay? But make sure you can answer that part correctly. Newton's law of cooling, if you had Miss Quick for Cal 2, then you did this in that class. If you had me, we didn't do it, but we do it in here. We'll actually study Newton's law of cooling in detail. According to Newton's empirical law of cooling, the rate at which a body cools is proportional to the difference between the temperature of the body and the temperature of the surrounding medium, called ambient temperature. Suppose that the temperature with respect to time denotes the temperature of a body at any time t, and T sub s is the constant temperature of the surrounding medium. This is the formula for Newton's law of cooling, which is most of the time a separable equation. Solve it by separation of variables. So these are just some models that I wanted you to see. Some we'll talk about in detail, some we might not. Since this is an applied class, we need to be able to apply as much as we can to real life stuff. When you guys get in engineering school, your teacher is going to see this class usually is your color. This class is the one that usually says if they can't pass this, then they can't go into their more advanced engineering courses. But the truth is, when you get in those engineering courses, the professor is going to go back and reteach what you need to know for that application. 9 times out of 10, that's going to happen, okay? Because they're not going to expect that you remember all the DE and calculus that you learned, probably. Now, let's do one more work together, and we will break, and then we will have the quiz, okay? And this one's going to prove to be more fun. Easier than this one was. So, next thing, let's have a break. Let's answer some questions here. One was from your homework set number 2. As to why something is linear or nonlinear. Well, this problem was the hardest one you guys had. Number 2, you had dy over dx equal to y times 2 minus 3x over x times 1 minus 3y. It actually it's easier for me to change that dy over dx to a y prime when I'm checking for linear or nonlinear. And I'm also going to multiply that stuff out there. So how about 2y minus 3xy? And how about x minus 3xy? So if I cross multiply now, I could say that I've got x minus 3xy times my y prime. And then I've got 2y minus 3xy on the right side. Now, when you're looking at linear or nonlinear, this all right here becomes the coefficient of your y prime. All of that is the coefficient of your y prime. If I factor out a y over here, I'd have 2 minus 3x left. Okay, so you know when we were judging linear or nonlinear, you can have y prime, you can have y double prime, you can have y triple prime, you can have y derivatives like that, ordered derivatives as high as you want. But you can only have one term that's just got a y coefficient, or a y term variable. This is that. There's your y variable. The coefficient
coefficient of your y prime, you cannot have a y involved in your coefficient of y prime. There's no way to get that y out. No way to get that y away from it. That is why that is non-linear.
Okay, what else? Any other questions you guys have got tonight before the test? Is everybody just wanting to dive in head first on this first test and see what happens? What about your direction fields? Do y'all remember how to do that? At each point, you plug your point into your derivative, your differential equation, find the slope, and you draw a line segment that's got that approximate slope to it. Yes, sir?
Do we have anywhere that the differential equation and then the directional field?
No. Did y'all notice, I told y'all only that you had to work last week. This first side of the homework is all you're really responsible for. Go ahead and do the second one this week because we didn't get into lecture 3. This still goes with what we did this week. All this still goes with it. So I thought it was neat after you can find the solution using separation of variables or whatever, that I've also pre-printed the direction field for the solution curve also. So it's pretty neat. You could actually graph the solution of it going through that specific point that's plotted in it. I've actually in my notes that I've got the solutions to this posted. But I've actually tried to draw in the solution curve for you to show you that it flows with the direction field that's given. All right, scratch paper. I reserve the right to check cheat sheets, and I may be walking around in a minute. I love yours, by the way. I'm not married to them. Color coding, highlighting. She's a type A personality, very organized. I had one guy come from Alabama one year. His cheat sheet was so immaculate, he couldn't make another 3 on a test before he got his cheat sheet. Good job, good job. So it has to be handwritten front, back, that kind of thing. Do y'all need me to give you scratch paper or do you have your own? Would you rather use your own line? Does anybody need scratch paper? I say scratch paper. If you need extra paper or anything, let me know. Did everybody get the take-home test? Not the take-home test. We'll take home worksheet. Let's do next week. Do Wednesday. Everybody got this? New Wednesday. Okay. So here's the test, front and back. Do good. Make 100. I hope to have them graded sometime by tomorrow afternoon. I'll post grades on Blackboard.
be in such a hurry that you miss silly stuff. Be careful.